Hello, and welcome to the third office hours. Let's jump right in.
All right.
So, many students, myself included, had some questions about the resampling wheel, and specifically when you draw a random number between 0 and twice W max. Where did that number, twice W max, come from?
I have the same question. I made it up.
Okay.
I want to make sure that the wheel can jump over an entire particle, so it wouldn't be large enough. But if you make it really large, then you have to search a lot. So I figured if it's 2n, that's going to be fine.
And does this bias the sample in any way, choosing this number?
I actually don't know. So
Okay.
I think there's certainly a correlation between adjacent particles in the selection of particles. So they're not independently drawn. I just don't know what the effect on the particle filter would be.
Okay, thank you.
And I wish I did.
The next question, or two questions I should say, comes from George Brindero. And he wants to know if there are any rules of thumb that we should keep in mind when we're choosing what filter to use for a given situation. So when do we use the particle filter? When do we use the Kalman filter?
Absolutely, yes. So the particle filter is the easiest to implement, but the complexity scales exponentially with the number of dimensions. And that's usually a problem because if you have a high-dimensional space, you just can't apply it. The Kalman filter is the only filter that doesn't scale exponentially, so it's very nice. So if you have like a 15-dimensional space, you will usually use a particle filter, but the problem with the Kalman filter is it's unimodal, so you can't really have multiple hypotheses. There's extensions of the Kalman filters that do this, called mixture of Kalman filter, multi-hypothesis Kalman filter. They can do this that address some of these problems. The grid kind of histogram filter is applicable in situations similar to the particle filters where you have like a global uncertainty, and it's more systematic. So in the particle filter, if you lose track of the correct hypothesis, you might never regain it. In a grid-based filter, you have a chance of regaining it. Grids are easily supported in many programming frameworks, so sometimes they're the better ones to use, but they also have a generic limitation in the accuracy, which is related to the resolution of the grid. My recommendation is if you have a multimodal distribution, use particle filters if you can. And if it's really a continuous space with a unimodal distribution, use Kalman filters.
Okay, that's a great segue into Ab Sherwin's question, which was about switching between filters on the fly. So, for example, we have our particle filter converges to a unimodal distribution, and then can we switch to the Kalman filter?
It isn't done much that people switch, and the reason is when you switch between filters, you end up getting moments of increased uncertainty. You can see this when you buy commercial GPS receivers. They tend to run multiple Kalman filters, turns out, depending on whether it's 2D or 3D navigation. When they switch, the behavior becomes a little bit iffy, and often is bad for robots because then they jump a little bit because this filter says this thing, that filter says the other thing, and they're not quite consistent. There is ways to combine multiple filter types, and the most common one is called a Rao-Blackwellized filter. Rao-Blackwellized, after Rao and Blackwell. What they found is that in a particle domain, sometimes if you nail certain dimensions with particles, everything else conditional on the particle becomes Gaussian or unimodal. And then you can exploit the efficiency of a Kalman filter that is now attached to individual particles. I'm not going to go into any depth here, but there's an entire field of Rao-Blackwellized filters that sometimes can estimate in the spaces of hundreds of dimensions.
Great, thank you. That actually predicted George Brindero's next question, so I'll move on. Drew Noakes wanted to know about what happens to a particle filter when the motion model moves a particle into an invalid place. So for an example, in that corridor demonstration you gave, what if a particle gets moved into a wall?
Well, thanks, Drew. Great question. The obvious answer is you kill that particle. And the way to think about this is, in the measurement model, you could have this kind of implicit sensor that says, I'm just sitting inside a wall. And the truth is, the robot would never sit inside a wall. So that sensor would always say with absolute certainty, I'm not sitting in the middle of a wall. So this kind of hypothetical sensor would justify that the weight of that particle that's in the middle of the wall would get weight 0. So you just kill it.
Okay. And a couple more questions from Drew. What about dynamically adjusting our big N, our number of particles, based when we want to trade off between like computational cost versus the accuracy of our filter?
So dynamically setting the number of particles has been done quite a bit, and it's a good idea under certain circumstances. Obviously, the fewer particles you have, the faster you can compute. If you're tracking really well and all the particles are centered on one location, there isn't really need to have as many around as when you're globally uncertain. The way to set the number of particles is often done by looking at the total non-normalized importance weights. So if all your importance weights are really large, then you're probably doing a great job tracking and you don't need that many particles. Whereas if your importance weights are all very small, then chances are you're doing a really lousy job tracking and you need more particles. That isn't perfect, so an unlikely measurement can cause weights to be small, but a good heuristic would be to say, let's particle sample until our non-normalized importance weights reach a certain threshold, and then let's stop sampling. Now, truth telling, many of the systems we're dealing with are real-time systems, and you can't really afford using many particles sometimes and few other times because there's a fixed amount of time between which you want to do your estimates. And then it's more tricky. But in principle, using few particles when you track well is a very viable solution.
Okay, thank you. Taka also had a question. He wants to know, distinguish between moving landmarks and non-moving landmarks. The maps that we dealt with in class were all static, and the landmarks were fixed.
Mm-hmm.
What happens, how does the Google car distinguish between these moving vehicles, moving people, and these static landmarks?
Yes, that's a wonderful question. First of all, the Google car assumes that the ground map, like the surface map of the street, is basically fixed. So if lane markers would move along a little bit, then the Google car would probably get confused. Little secret here, so please don't repaint your lane markers when the Google car comes by. That's treated differently from stuff that sticks out of the ground, and even that is used as a landmark. What we do is we have a threshold, a probabilistic threshold that says what's the chance of this thing being mobile or not. And we do this by establishing correspondence, which means we take measurements a time step earlier and measurements time step later, see which is the most likely correspondence between these two measurements, and then see if there's a motion vector in between. Sometimes we can explain the way by just noise, but for cars and people and so on, there's very often a very clear and strong motion, in which case we assume this thing is moving on tracking. It also turns out that the way we build our prior maps is sometimes we drive by multiple times, we do differencing, and then we have mostly captures of static things in our maps. We happen to know that in the middle of a street, there tend to be no static things, there tend to just be moving things. So we can bias the estimate towards saying, well, on the middle of a street, whatever you see is likely not static. And tossing this all together gives us a fairly good tracker.
Okay, thanks a lot. That's all we had for this time.
Mm-hmm.
And we'll see you all next week.
But I want to make a comment. I hear that many people really positively received the homework assignment on particle filters, which is great. It took me a while to make it. There's also on the discussion forum, there's a posting of a graphical version of it, and I downloaded it. It looks really great. I couldn't get the cursor keys to work on my computer, but it's really great basis to visualize. And I think particle filters are really hard to understand without visualization. So I'm really sorry that our current program environment doesn't provide visualization. I hope in the next round we'll fix that. I'm pretty sure we'll fix this. So please play with it. The other thing I noticed in the discussion boards, and I wanted to call for feedback on the same Facebook group, that people want harder homework assignments. I'm not sure that's true universally. So if you have an opinion, why don't you just post it? I'd like to get a sense of it. I'm thinking of making an assignment where we toss everything together and really build like a mini version of an actual car. That's going to be really involved. So let me know what you feel like. I mean, this course right now, I would argue, is really Stanford caliber. What you guys are doing and your girls are doing is really at a quality that I would expect my best Stanford students to do. The type of things you implement certainly is at the same pace I teach at Stanford and possibly faster. But if I go to a general kind of build a little robot example, then I'm going to exceed beyond Stanford pace. So it's up to you. Let us know.
All right, keep us posted. I'll be reading the forums. I'm sure Sebastian will too. Thank you very much, and see you next week.
All right.